Welcome to this first lecture of Math-S401, which is the course Dynamic Optimization. So in this course we're going to see the problem of discrete time dynamic optimization. We're going to see the theory behind these kind of problems, and then we're going to also see how we can use computer programs in order to solve these problems or in order to simulate the solution to these problems. So in the first lecture, I'm going to outline the general problem that we're going to try to solve during these lectures. I'm going to give an example, and I'm going to show several approaches that one might take in order to solve this problem. And in the end, we're going to arrive at a useful concept that we're going to investigate during the next couple of lectures, which is going to be the Bellman equation. So the course is on dynamic optimization. So dynamic optimization contains two words. Okay, so the first is dynamic and the second one is optimization. So dynamic points to the fact that we're looking at problems that involve time. Okay, today, tomorrow, in a year, maybe in 100 years. So time in general. And then optimization points to the problem that we have a problem and we want to find the maximum of the minimum of some kind of objective function that involves time. Okay. So in general, we're going to look at maximization, but you can also look at minimization problems. This is also part of dynamic optimization. So when relating to time, there exist two kinds of dynamic optimization problems. So the first one treats time as being something that's continuous. Okay, so this means that time is some element in the real numbers. Okay, so you have 1, 1.5, 1.2, right? So time progresses in a continuous fashion. And then there is a second kind of problems where time is treated as a discrete concept. So you have time at point 0, you have time at point 1, time at point 2, and so on. Okay, so there's only countable many periods. When you talk it in a mathematical way, for discrete there's only countable many periods. For continuous there are uncountable many periods. Okay, if you know the difference between countable and uncountable, basically for discrete time is an element of n, in continuous time is an element of r. Okay, the real numbers and the natural numbers. So in this lecture we're going to focus exclusively on discrete time dynamic optimization models. So discrete time dynamic optimization models have some advantages. So the first one is that you can use more easily the concept of what we will use as Bellman equations. And so this is the main mathematical tool that we will use during these lectures. The second one is that also for discrete time dynamic optimization, it's more easily to implement them on a computer. Right? If you work with continuous time, you have to use finite approximations anyway. So basically, because computers cannot handle continuous variables, you have to resort to discrete settings anyway. And then in this case, discrete time optimization models are a bit more easy. So you have continuous and discrete. You have also a second distinction, which is has to do with the time horizon over which we see the problem. And in this respect, you have finite horizon problems. So this means that after some period of time, the problem stops. All right, so you only look a finite number of periods ahead, and then you of course have infinite horizon problems, which basically means that we have a problem where time never ends, right? So you look at the problem, you have a problem that starts now and goes on forever. Okay. So for the start of this lecture, we will be mainly focusing on infinite horizon problems. In the second part of the lecture, I will also look at some finite horizon dynamic optimization problems. Okay, but so far, to start, we'll look at infinite problems and in discrete time. All right, so we're going to focus our main attention to one particular type of problems. So let me write it down, how this problem looks like. So we maximize something. This is the optimization part. And let me say that we're going to maximize over some variables. The first one is called A0, the second one is A1, A2, and so on, right? There are infinitely many A's that we're going to optimize over. What are we going to optimize over? It's going to be a sum that starts at t0 and goes to t infinity of beta to the power t of some f that's a function of xt at, right? I'm going to explain in a minute what all these things mean. And then we're going to have several constraints. All right, the first constraint is going to be that at is in gamma of xt. The second one is going to be that xt plus 1 is equal to r of xt at, and then there's third restriction is that x0 is given, right? It's some variable that we know the value of. All right, so let me now explain a little bit more in detail what all the different parts, all the different ingredients of this maximization problem are. So we're going to start with looking at the x's, okay? And we're going to say, now I haven't defined what these x's are, right? So we're going to assume that all the x's are in some set x, right? Big set x, and this big set x is the set of all states, right? And the state is here, you can see it as a state of the world, right? So it's basically a description of the world today, okay? At least that's a description of the world today, everything that's relevant for the model that you're trying to have a look at. Okay, then xt is the state in period t, right? So time is discrete, you have t1, t equal to 1, t equal to 2, t equal to 3. So x1 is a state in period 1, x2 is a state in period 2, and so on. Okay. So we have states, and then we have also x's, we have also a's. Okay, and you assume that all the a's are elements from some set A, and A is the set of all actions. Okay, so an action is something that the decision maker, the person who wants to solve this problem, is going to be able to take. Okay, so A of t is then the action taken in period t. Okay, and notice here we're maximizing over A0, A1, A2, and so on. So basically we're trying to find the actions that maximize our objective, which is this thing here. Okay, and then there's some constraints on how the actions and the states are. Okay, so now let's look at the third thing. The third thing here is this f, right? And you see that f takes a state and takes an action. Okay, so f is going to be a function of x times a, right? Going to take a state and action, and it's going to give us a real number, right? So it's a real valued function, and you call this f the instantaneous payoff function. Okay, so it's the value, so f of xt at is a payoff that you get in period t when the state is xt and the action is at. Okay, so payoff in period t when xt is state and at is the action. Okay, here in the objective function you also have a beta, and beta is going to be a number between 0 and 1, and this is the, maybe you already know it, this is the discount rate. Okay, so in period t this is the payoff that you have, right? But this is only obtained t periods in the future. Okay, so in order to bring it to today's present value, you have to discount it, and you discount it by a factor of beta every period. So beta to the power t is indeed the amount of payoff that you get in period 0. Okay, so this is how it works. So basically this is what we try to maximize, and we try to find the actions A0, A1 and so on in order to maximize this thing here. So let's have a look now on the constraints that we have here. Okay, so the first constraint says that AT should be in gamma of xt. Okay, so what's gamma here? Gamma is going to be a correspondence. So it takes a state in X and it gives you a subset of A. Okay, so correspondence is something that eats an element and outputs a subset of something. Okay, so it's a generalization of a function. If you're not familiar with correspondences, you can also always look at my lecture video of Math-S401 on correspondences to get a better idea of what these concepts are. So gamma of X is the set of actions that we can take, or that the decision maker can take when the state is X. Okay, so dependent on the state xt, it might be that you can take different kinds of actions. Okay. Some actions may not be available because today it's raining. Some actions may be available when it's raining and not when it's there's sun. Okay. Okay, so this is the first constraint. So in some cases we're limited on the actions that we can take. Then the second constraint says that xt plus 1, right, so this is the state in the next period, is equal to r. This is a function of the state today and the action taken today. Okay, so r is here a function, it takes a state and it takes an action and gives us a new state, so it goes to X. Okay, so Rx of A is the state tomorrow if X is state today and A is the action today. Okay. And then the final thing is that x0 is given. Okay, so x0 is a state, right? It's a state at period 0. So period 0 could be today. So today I know what the state of the world is. Okay, so why do we need x0? Well, we have to start from somewhere. Okay, so if you look at this process, how can you picture this? Well, we start with the state x0. Then what's under the control of the decision maker are the actions. Okay, so the decision maker takes an action A0, and this is an element of gamma x0, right? So gamma, I know gamma, so I know which kind of actions that I can take, so I pick an element in the set. And then if I have the state and this action, this R function, R is also called the law of motion. Okay, sometimes you see this kind of name. Then my R function is going to determine the state tomorrow, right? This is going to determine x1. Okay, because of x1 is equal to R x0 A0. Then when I have x1, well, next I take an action in gamma of x1, and then x1 together with A1 is going to determine the state x2, 2 periods ahead. Then I take an action A2 and gamma of x2. These two ingredients, x2 and A2, is going to determine x3. I take an A3. This is going to determine x4, and so on and so on. Okay, so this is basically how the process. You start with a state, you take an action, this determines a new state, then you take an action, this determines the next state, you take an action, and so on. So this R function here is what we call deterministic, right? Once we know the state and the action, we are definitely sure what's going to be the state tomorrow. For some programs, this is going to be a stochastic process, right? So there's going to be some uncertainty about the state tomorrow. So we're also going to treat these stochastic dynamic optimization problems, but this is for much later on in the course, right? So first of all, we're going to focus on a setting where R is known, right? Is deterministic. Okay, so here we have the different ingredients. We have the state space, a set of all states. We have the action space, set of all actions. We have an instantaneous utility function, which is the thing we're trying to optimize. We have a discount rate. We have a feasibility correspondence. Okay. Feasibility correspondence. That determines what I can do today, given the state today. And then we have law of motion that determines the state tomorrow, given what I've done today and what's the state today. Okay, so this is the general form of the dynamic optimization problem that we're going to see. And notice here that time goes from 0 to infinity, right? So it never stops. Okay. So let me give an example, and this is going to be the Gauss-Koopman model, right? So it's the I think most basic optimal growth model in economics. So what do we have? Well, let me go to the different ingredients. Now the state space X is going to be the set of capital stocks. Okay, so you have a model where you have capital accumulating over time, and every time period you're allowed to consume something of this capital stock, and the rest is going to enter a production process to determine the capital stock next period, and then you're going to be able to consume some part, invest some part, and so on and so on. Okay, so this is the model that we're going to look at. So the state variable is going to be determined by the level of capital. Okay, and we're going to call this K. K is going to be the level of capital. Capital cannot be negative, so we're going to equal X equal to R plus, right? Any real number, non-negative, can be a capital stock. And what are we going to decide upon? We're going to decide upon the level of consumption. So A is going to be set of consumption levels, and we're going to denote consumption by C. And again, we're going to assume that consumption cannot be negative, so we're going to look at R plus. Okay. Then we need an instantaneous utility function, right? This F here. And for this, what are we going to try to optimize? So this is a representative consumer model, so we're going to try to optimize utility. So my F is going to be utility, right? And we're not going to denote this by F, we're going to denote this by U. And in this case, U is going to be a function only of consumption. Okay, so in general, we had that F was a function of both the state K and the action C. But now in this model, it's only going to be C, right? So you see that this is more general than this particular form here, which is okay, right? You can be more specific. And in this particular model, I'm going to use the log function. So this is going to be ln C, okay, which is a utility function, one kind of utility function. And then you have the beta, right? So this is going to be simply going to beta, is going to be the discount rate. And then we need to look at the different constraints. So let's first look at the law of motion, right? Maybe this is easier, or R function. So our R function is going to take a capital stock, it's going to take a consumption level, and it's going to give you the capital stock in the next period. Okay. So capital stock in the next period is KT plus 1, and you would like to write this as a function of KT and a function of CT. Okay, capital and consumption today. So capital today, we're going to use this in as a production. So we need to specify a production function, right? So in general, you can write this as f of kt. This is going to produce an output, and from this output we're going to eat something. So this is going to be ct, and whatever is left is going to be the capital stock of tomorrow. Okay, and here we're going to use a very easy production function. So we're going to specify fkt as a times kt to the power alpha minus ct. Here alpha is going to be a number between 0 and 1. Okay, so this is going to be our law of motion, and from this we can easily derive our gamma of k, right? So gamma of k is all consumption levels that we can consume given that k is a capital stock. So we know that c has to be greater or equal to 0, right? So what's the maximum amount that we can consume? Well, the capital stock tomorrow has to be non-negative, right? So the maximum amount of ct that we can consume is equal to f of kt. Okay. So c has to be between 0 and f of kt. So this is gamma of kt, is this interval here. Okay. And if you use this value here, well then this is equal to 0 akt to the power alpha. Okay, this interval. Okay, so in some cases this gamma can be derived from the law of motion and on the restrictions that we imposed initially. In some other cases it cannot, right? So this might even be smaller. If you say, okay, maybe I cannot consume more than 1000, right? Then this upper bound has to be the 1000, right? So you can say, okay, I cannot eat more than 1000 euros of worth, then there's some other ceiling. But in general, okay, we're going to keep it like this. Okay, so this is the problem. So given all these ingredients, how does our problem look like? Well, we're going to maximize. So what are we going to maximize over? Well, over all consumption levels. Should be ct, c0, c1, ct, and so on, of a sum, right, from t0 to infinity of beta to the power t of ln ct, right, instantaneous utility function, and then subject to kt plus 1 is equal to a kt to the power alpha minus ct. You need that kt is greater or equal to 0, right? And this immediately imposes this constraint, right? So you don't need to impose it separately. And oh, I forgot one important thing, right? x0. So here x0 is going to be k0, the initial capital stock is going to be given. Okay, so this is the problem that my intertemporal utility maximizer is going to solve. Okay, so as we have seen here, so what do we have? We have an initial state. I'm going to choose A0 in order to maximize this entire optimization problem. I'm going to get x1, then I'm going to choose A1 in order to solve this problem, right? So all these variables are going to be chosen in order to optimize my problem, and all these states are obtained from the previous period, right? So the only thing that can change is the initial state, okay? Because these are chosen in order to optimize, and these are a consequence of this optimization choice. All these will be endogenous, right? This will be determined by the sequence of A's. So the only parameter in my problem here is x0. Okay, so this means that the solution of this maximization problem will depend on the functions and on the beta and on the gamma and on the r. But apart from this, the only parameter here is x0. Okay, so the value function, the number that I will get out of this problem, if I can solve it, right, I will get the number here, which is going to give me the value of this maximum, is only going to depend on x0. Okay, so it only has a single parameter. Similar here, the value that I will get out of it, the number that will solve this problem, is only going to depend on k0, the initial capital stock. Okay, and we call this the optimal value function, which is a very important concept in dynamic optimization and in optimization in general. Okay, so now you have this optimization problem, so you can ask yourself the question, how do we solve it? And normally you say, okay, I have an optimization problem, how do I solve it? Well, there exists no methods here, right? I can set up the Lagrangian. If all these have nice shape restrictions like concavity and so on, I can take the first order conditions, try to solve the first order conditions, and then I get the solution to my problem. Right, so the Lagrangian standard way of solving optimization problems. You may think, okay, this is a good approach to solve this here. Of course, there's a catch. The catch here is that we need an infinite number of things we're optimizing over. Okay, and in Lagrangian optimization, normally you only have a finite number of decision variables, right? So you have a finite number of first order conditions. Here you will have infinitely many first order conditions. And if I look at the proof of Lagrangian optimization, nothing says to me that this will also work for infinitely many decision variables. But we can try, and we can say, okay, here I go from 0 to infinity. What would happen if I take a finite time horizon? Maybe I can learn something here, right? So let the time horizon, right? So I'm going to restrict here this problem. Instead of infinite time, I'm going to take only finite time. Okay, so let's, for example, limit the time horizon to period 0. Well, what's my objective function in this case? Well, I'm only going to maximize over C0. Okay. My objective function is going to be beta to the power 0 first period, which is equal to 1. And then I'm going to have log of C0. Then K1 is going to be equal to a K0 to the power alpha minus C0. There's no C1, right? So K2, I don't care. C0 is going to be greater or equal to 0, and K0 is good. Okay, and let me call the solution here V1 of K0, V0 of K0. Here the 0 is because this is a different problem than this one, right? So it's time is limited to 0. Okay, and we can try to solve this problem. Here it's not super difficult, right? So what's the thing here? Well, for this problem, K1 doesn't enter the objective anymore, right? There's no second period. So the best thing that you can do is put it equal to 0, right? Because this will maximize my C0. And I care about C0 because I want to maximize my utility. Okay, so it's going to be optimal to put K1 equal to 0 in this problem. And if I do this, then C0 will be equal to AK0 to the power alpha. So my V0, K0 will be equal to log of AK0 to the power alpha. And this is equal to log ln A plus alpha ln K0, right? So I have explicit solution to my value function in this period. Okay. This is a very easy problem. Let's go one period ahead. Okay, and in this case, I'm maximizing over C0 and C1, ln C0, and then the first period, I'm going to have beta. Second period, I'm going to have beta ln C1. And then the law of motion is going to tell me that K1 is equal to A K0 alpha minus C0, and K2 is going to be equal to A K1 power alpha minus C1. C0, C1 is going to be greater or equal to 0. And k1, k2 also, right? And then k0 is given, and if I solve this, I have v1 of k0. So how do I solve this here? Well, c1 and c0 are in my objective functions. After I've chosen c1, I have k2 left, but I don't care about the second period, right? So the best thing that I can do is put k2 equal to 0. Okay, so if k2 is equal to 0, then I know that c1 is equal to a k1 alpha because of this second law of motion, and c0 is equal to a k0 of alpha minus k1. Okay, so what we're going to do now is going to plug this into our objective function. So now we're going to try to max ln a k1 alpha plus beta ln a k1 alpha minus k1. No, sorry, I switched c1 and c0, so it's ln a k0 alpha minus k1 plus beta ln a k1 alpha. Okay, and we're going to maximize this, and here we chose c1 and c0 but because of the substitution we lose one of the two variables, so we're going to maximize this with respect to k1, right? This is fixed, this is the only free variable in this maximization problem. So we can try to solve this using standard first order conditions, right? So the first order condition here is going to give me that 1 over a k0 alpha minus k1, and then the chain rule is going to change this as minus 1 plus beta, and then a k1 alpha, and then the chain rule a alpha k1 alpha minus 1, that this expression is equal to 0. Right, we can put this to the other side, get rid of the denominators, and then we have a k1. Okay, so maybe first simplify here. The a drops out. This alpha drops, this disappears. So we have minus 1 a k0 alpha minus k1 plus beta alpha over k1 is equal to 0. Okay, and now put this to the other side. We have beta alpha a k0 to the alpha minus beta alpha k1 is equal to k1. So beta alpha a k0 alpha divided 1 plus beta alpha is equal to k1. I think this is what it should be. So what we can do with the solution, we know that this is equal to v1 of k1. So we can plug it in here, the solution of k1 that we have found. Then we obtain that v1 k0 is equal to ln a k0 alpha, and then minus beta alpha a k0 to the power alpha divided by 1 plus beta alpha plus beta ln a beta alpha 1 plus beta alpha to the power alpha, and then also multiplied by a, and then k0 to alpha. Okay, I think should be something like this. It's possible that I made a small mistake. So anyway, here I have separating the k alpha 0 with the other terms. It's a minus beta alpha 1 plus beta alpha, and then I have plus alpha ln k0, and then here I have plus beta ln a beta alpha a 1 plus beta alpha alpha plus beta 2 alpha ln k0. Okay, so in the end what I arrive here is with some fixed number, right? Let me call this a something, and then plus can take alpha outside, and then I have 1 plus beta alpha. No, 1 plus 2 beta ln k0, something like this. Okay, so I have something times plus something, let's call this b times ln k0, right? So I have something that's linear in log k0. So in principle, we could also look at t equal to 2, we could look at time period t equal to 3, and so on, and we can solve this for every time period over and over and over again. Of course, these will become longer and longer and longer. I'm not going to work this out. I think the lecture notes has it for t equal to 2. So what do we have then? Well, then we have an expression for v0 of k0. You have an expression for v1 of k0. You have an expression for v2 of k0, for v3 of k0, and so on. And then in the end, we hope that maybe these things converge to something, right? So in the limit, we would like to take t going to infinity and then hope that this converges to something. And in our case, actually, it does converge to something. So v alpha of k0, you can show that it takes the form a plus, let's call it a plus b times log k0. So it's still linear in log k0. And in the limit, this alpha is going to be an expression, sorry, this a here, which keep on willing to write alpha, but it's a. So a and b have a known expression, so b will be equal to alpha 1 minus alpha beta, and a will be equal to a somewhat complicated expression is 1 minus beta, and then ln a 1 minus alpha beta plus alpha beta over 1 minus alpha beta ln a alpha beta. Okay, you don't need to know this by heart. In fact, it doesn't mean so much. But the interesting thing that it's still linear in ln k0, right? So it does converge to something, and it converges to this. So the question is now, is this actually the solution to the infinite horizon optimization problem? And you can show that in this case, actually it is, right? So in this case, this actually converges to this optimization problem. So you can say, okay, this is nice. So what's my solution method going to be? Well, I'm going to solve my problem for t equal to 0. I'm going to solve it for t equal to 1, for t equal to 2, 3, 4, 5, 7, and so on. Very big numbers, and then I'll see if this converges to something. So there are a couple of problems with this approach, right? So this is the whole aim of this exercise, is to go over these potential problems. Is that, well, first of all, in this case, we had expressions for v0 and v1, v2, and so on, right? So we had a couple of first order conditions, and in some way, because we were lucky with the functional forms, we were able to solve them and substitute them back into the objective function, right? So, but in general, I'm not sure that I will always be able to do this, right? So it's not always the case that we have closed form expressions for v of, let me call this vt of k0, right? It's not always the case that we can actually write this as a function of k0, right? Okay. So the second thing is that we said, okay, we look if this converges, but who tells me that this will always converge, right? Is this some mathematical law, or is there some reasoning behind this? So will this always converge, right? So in general, I have no reason to think that these set of solutions will converge to a limiting solution. Okay, and even if it converges, well, then we have a limit of the solutions. Well, the limit for t going to infinity of the solutions for t finite. However, what we want is the solution of the limiting problem, right? We want to have the solution for when t is infinity, right? And I have no idea if these two are equal, right? Is the limit of the solutions also equal to the solution of the limiting problem, right? So these two may be different things. Okay. There's a fourth problem, and this is more from a computational perspective, you may say. Okay, so this is a very cumbersome procedure, right? You have to solve it for this, you have to solve it for period t1, you have to solve it for t equal to 2, and so on and so on. So you have to solve the same problem over and over again many times, and then hopefully you see some convergence going on. So this is a very annoying process, and if this was the aim of teaching you dynamic optimization, it will be a very maybe not boring lecture, but will be very cumbersome lecture, right? Because you have to solve optimization problems over and over and over again. Okay, and then there might be a fifth problem. I think there are several others, but I will keep to 5. So here we have a limit of the solutions, right? So even if this converges to a solution of the limit, we don't know if the solution of the limit is unique, right? There might be multiple. I don't know. Maybe there are multiple value functions that solve this problem, right? So maybe here we find one solution, but there might be other solutions, right? And it might be the case that for these other solutions, we will never be able to find them according to this method. Okay, so this just lists a couple of problems that may exist when using this procedure. So we're going to see 2 other procedures to potentially solve this problem. But first, we're going to take a break. So, welcome back. And in order to discuss the potential other solutions that you can use to solve our problem, let's go back to the flow of the problem. So we started with an initial capital stock K0, and from this we chose some consumption level. Okay, and that's then using the law of motion. If we combine these two, then we get the capital stock at period 1. Then our optimal decision maker chose the consumption level C1. This gave us the capital stock at period 2. We chose level C2. We got the capital stock at period 3. We chose C3. We have the capital stock at period 4. We chose C4, and so on and so on. Okay. So if we look at this entire problem, okay, this entire horizon, this corresponds to the following optimization problem where we want to maximize with respect to C0, C1, and so on. T equal to 0 to infinity of beta to the power t of, it was a utility, so ln of ct. And then we had some constraints. Basically, the most important one was the law of motion kt plus 1 is equal to a kt alpha minus ct, and then k0 is given. Okay, so this is our maximization problem, and here this gives us the value function v of k0. So now let's assume that we have taken c0, and together with k0 we arrived at q1, right? So now we have a decision maker, right? So at t equal to 0, this is his problem, determining c0, c1, and so on. and assume that we're now at period t equal to 1, so he has already made the decision C0, right? So now we have this problem. So what's this problem? Well, we know K1, right? Because this is already determined here, but this is in the past. So we know K1. So now the decision maker has to decide on C1, C2, C3, C4, and so on and so on. Okay. And this determines then K1, K2, K3, and so on. So if you only look at this period here, now the optimization problem of our decision maker is to choose C1, C2, and so on, right? Because C0 is already decided on. I don't have to maximize to it anymore. Of t equal to 0 to infinity, of beta, no, t equal to 1 to infinity, right? Because we're starting at period 1. Of beta t minus 1, right? Because this is the present, this is tomorrow, this is in 2 days, right? So you have to shift one period. Of ln ct, and then you have the same kt alpha minus ct. And now it's not k0 that's given, but it's k1 that's given. Okay, so this is the problem at period 1 for the decision maker, right? So if I compare this problem with this problem, basically there's not much difference, right? So from a formal point of view, these two problems are identical. Okay, if I shift everything here with one period backwards, I basically have this problem. Okay, so the only difference here between these two problems lies in the parameter k, because here I start at k0 and here I start at k1. Okay, so if I look at the similarity between these problems, then I have to convince myself that this is the same as the value of the same problem as I have here, but now instead of starting at k0, at k1. Okay, so this is the problem here. Okay, but now I can do something very interesting. Basically, I can take this problem here and substitute it in this objective function here. Okay, so let me take this here. I have v of k0. So this is the maximization over C0, C1, and so on. So what I can do is I can take first maximize over C0 and then maximize over C1, C2, and so on and so on. Okay. So this is what I'm going to do. I'm first going to maximize over C0, and then I'm going to maximize over C1 and all the future periods of this here. So this is beta to the power 0, which is 1 of ln C0 plus beta of t equal to 1 to infinity of beta t minus 1 of ln ct. Right, so basically here I taking one beta out of it, and then I have an exponent t minus 1. Okay, and then the constraints kt plus 1 is equal to a kt alpha minus ct, and then k0 given. Okay, the law of motion and this here. And now you see that this here is basically the same as this here. Okay, so what do I have here? I maximize over C1 until infinity. The first term here is ln C0. I'm not maximizing over C0, right? So basically I can take the first part before the second maximization problem. Then I'm maximizing over this thing here, which is basically the same as this. And because C0 is maximized over in the second round, it's basically conditional on K1. Okay. So what this gives us is the following. V of K0 is equal to maximize of C0 of ln C0 plus beta, and then the maximum thing that I can do in the future, right, which is V of K1, right? It's basically substituting this in here. And then of course I have the law of motion, which says that k1 is equal to a k0 to the power alpha minus c0, and k0 is given. Okay, so what does this tell me? Instead of doing this, choosing C0, C1, and so on, what I can do is first I can solve the problem in period 1 forwards, given a possible choice of C0, right? Because notice here that K1 is a function of C0. If I change C0, I will change K1. But this has to be optimal, right, for the future. And then I choose C0 given that what I'm going to do tomorrow is going to be optimal. Okay, so this is the idea behind this expression here. Notice that if I chose C0, I'm going to have to take into account that C0 influences my instantaneous utility function, but C0 also, via the law of motion, is going to influence K1, and K1 is going to influence my future utility, right? My future payoff. This is basically the payoff that I'm going to get from tomorrow onwards, right? So if I maximize with respect to C0, I'm going to have to take into account that C0 enters here, and then via the law of motion also enters here, right? So it's not, you cannot put this bracket here, right? So you have to take into account that it's also part here. So this gives you the intuition behind this expression, right? It's not a full mathematical derivation. And actually showing that this is equivalent to our initial infinite horizon optimization model, right? This thing here is going to take a long part, is going to deserve a mathematical proof, right? And this is actually what we're also going to do. We're going to prove that this is actually equal to this under some conditions. Okay. Let's have a look here at this equation. So this equation here, this is called the Bellman equation. So here I've written it for the Koopman model, the growth model, but in general it can be written like this, right? So V of the value function, depending on the initial state, is going to be maximum A0 of instantaneous utility fx0 A0 plus beta of V of x1, and then subject to the constraint that A0 is in gamma of x0, and that x1 is equal via the law of motion of Rx0 V0, right? So this is the general form of the Bellman equation, and this is for the optimal growth model. Okay. So notice here that my V function, this is my optimal value function. This is actually the function that I would like to know, right? I would like to find out what this function is. Is it quadratic? Is it linear? What are the coefficients, and so on? Okay, so this is my object of interest. And here the V function is here on the left-hand side, but it's also on the right-hand side, right? So the arguments that you put into it are going to be different, but the V function is here and the V function is here. So this is like an implicit equation. And then there's the added difficulty that we have to take into account, the max, right? So this is basically a function, max function is going to give me a function of the function that I want to find, right? So this is what we call an implicit equation. Okay. So here the argument is x0, right? So on the right hand side the x0 is here, and it's also here, and it's also here, and I'm going to maximize a0. So a0 probably will be a function of x0, and the a0 is here, it's here. Okay, that will influence x1, and here the x1. Okay, so everything is connected to each other in some sense, but it remains the fact that this function is on the right hand side, and it's also on the left hand side, right? So it's not like I can immediately solve this problem, right? This is an implicit equation. However, we would like to find out how to solve this problem. How can we solve this implicit equation or condition? So in mathematics, there's always an easy way to solve a problem, and easy in the sense of easy in theory. And the easiest way to solve a problem is to guess. Okay, why is this an easy solution? Well, you guess. If your guess is correct, then you have found the solution, and then you can stop guessing, and you can stop looking for a solution because your guess was right. It's a bit of an annoying solution because it doesn't give you an idea how to guess. Okay, but it's a valid method. Let's make a guess. And you already have seen previously. Let me look in my papers if I can see it. No. Well, anyway, we have solved the problem. So let me write back vk0 is max of c0 of ln c0 plus beta v k1. Okay, so this was my Bellman equation, and then k1 is a k0 to the power alpha minus c0, and k0 given. Okay, so this is my Bellman equation for the growth model. Let's make a guess, and you already have tried to solve this model for time horizon 1, time horizon 2, time horizon 3, and you have seen that this converges to something, and the form of this solution was something like a constant plus some parameter times ln k0. Okay, so this is going to be my guess, and it's a well-educated guess, right? Because you already have, I already told you that this is actually going to be the solution, so let's now verify that this is actually a solution. So what I'm going to do, I'm going to substitute it here, and I'm going to substitute it here. Okay, so on the left hand side I will have that a plus b ln k0. Actually I have to omit the k0 here because this holds for every k, right? So it's for all k I have this value. This is going to be have to equal to max of c0 of ln c0 plus beta, and now I can substitute it also here, but now it's not k0 but k1. Okay, a plus b ln k1, and k1 is equal to a k0 alpha minus c0, k0 given. So let me substitute k1 here in this function. So I'm trying to maximize the 0 of ln c0 plus beta times a plus beta times b of ln a k0 to the power alpha minus c0. I have a simple maximization problem with respect to c0, so I use first order conditions. I have 1 over c0 plus beta b, and then a k0 to the power alpha minus c0 times minus 1 is equal to 0. Okay. I can put this on the other side, try to get rid of the denominators. We have a k0 to the power alpha minus c0 is equal to beta times b times c0. So the optimal level of consumption is going to be a k0 to the power alpha divided by 1 plus beta b. Okay. So I know the optimal solution c0. Let me plug it back in. So we have that the left hand side is a plus b ln k0, and this is going to be equal to ln c0. So this is ln a k0 to the power alpha 1 plus beta b plus beta a plus beta b ln k1. Now I have to see what k1 is. So k1 is a k0 to the power alpha minus c, but I know what c is, so minus a k0 alpha 1 plus beta b, and this is putting on the common denominator 1 plus beta b of minus beta b a k0 to the power alpha. Okay. It's a plus, sorry. So let me put it here, beta b a k0 to the power alpha 1 plus beta b. Okay, so this is what I have. I don't have a max problem anymore because I already have the optimal solution. Okay, I've substituted in the objective function, I get this expression. So I can rewrite this, so a plus b ln k0 is equal to ln. Let me try to put the k0s separately. So I have a 1 plus beta b, this is a fixed, plus beta a plus beta b ln beta b a divided by 1 plus beta b, and then I have here alpha ln k0, and I here plus beta b alpha ln k0. Okay, so this here together is equal to alpha 1 plus beta b ln k0. So this here and this here. So what do I have here? Sorry, here I have a plus b ln k0. Here I have a constant plus an intercept times k0. And notice that this holds for every parameter value k0, right? Because we have assumed the function v to take this form for every k. So this has to hold for every k0, right? If I change k0, then it also has to hold. If I change double k0, it also has to hold, and so on and so on. Okay, so this fact that this holds for every k0, it means that this coefficient a has to be equal to the first coefficient here, and the second coefficient beta has to be equal to the slope here. Okay, so equating coefficients, I have that b is equal to alpha 1 plus beta b, and I have that a is equal to this entire first expression. A is equal to ln a 1 plus beta b plus beta a plus beta b ln beta b a 1 plus beta b. So this allows me to solve for b. Okay, so b is equal to alpha divided by 1 minus alpha beta, and then I can substitute b in here and I can solve for a, right? So I have 1 minus beta a is equal to ln a 1 plus beta b is 1 plus beta alpha over 1 minus alpha beta. This is already on the other side, plus beta alpha 1 minus alpha beta ln beta alpha 1 minus alpha beta, and then 1 plus beta alpha 1 minus alpha beta, and then we multiply by a. You can simplify this a little bit, so a is equal to 1 over 1 minus beta of ln. Here in the denominator I have 1 minus alpha beta plus alpha beta is just 1 over 1 minus alpha beta, so I have 1 minus alpha beta times a, and then I have beta alpha 1 minus alpha beta ln. So here I have the same thing, but this gets rid of this, so I have beta alpha a. Okay, And then I have to probably divide this by 1 minus beta or something. Okay, I'm not entirely sure that everything is working out, but in general we see that we have two equations and two unknowns, and we can solve this. So this indeed is a solution to the problem, and I can explicitly compute A and B. Okay. So indeed, yes, guessing sometimes gives me a solution to the problem. Guessing, of course, is difficult, right? Because you can keep on guessing until you run out of time or run out of motivation. So we're going to see a different kind of method to solve these, to solve the Bellman type equations. Okay, so let's return to the Bellman equation. V times K0 is equal to maximize C0 of ln C0 plus beta V K1 subject to K1 is equal to A K0 alpha minus C 0. Okay. So anyway, what we can do is we can make some kind of guess. Okay, and let's make an initial guess, and let's call this initial guess V0. Right, so V0 is a function of K. This is my initial guess for this value function. For example, it could be the constant function, or it could be a linear function, or some quadratic function. Okay, so I don't really care, I just make a certain guess. So for example, my initial guess is this is 5 independent of K, so it's just a constant function. So what can I do then? Well, I have an initial guess. I can try to plug in this initial guess here. Right, and if I do this, I get a maximization problem. ln C0 plus beta V0 of K1. K1 is equal to A K0 alpha minus C0. Okay, so because I know V0, right, I have made a guess, I can solve this problem. And if I do this for every K0, I obtain a new function. Right, which is similar to this value function, but now instead of V, the true V that I want to find, I just used any guess that I want. Okay, so in general, what comes out of this will not be equal to this function that I want. So let me call this V1. Right, that's the result of my putting my guess on the right hand side. So this gives me a new function V1. Okay, and by varying K0, I can get this entire function V1. Right, so I started with some function and I got a new function. And if these two functions are the same, well, then I know it solves this Bellman equation, so I'm happy. Right, I have found a solution. So if V0 is equal to V1, if this two entire functions are the same, well, then I'm very happy and I can stop. Right, I have found a solution to my Bellman equation. So if they're not the same, well, I can repeat this argument, right? So here I put it V0 on the right hand side, and I got V1 out of it. So I can take my V1 and plug it on the right hand side again. V1 of K1. So I have this problem. And I can again solve it, because I know this function, there's no uncertainty anymore, or there's no unknowns anymore. I can solve this problem, and I get a new value function out of it, which is now going to be called V2. Okay. And if V1 is equal to V2, then this solves my Bellman equation, so again, I'm happy. If not, well, I can keep on iterating this procedure. So I have a new problem now with my function V2. K1 is equal to A K0 alpha minus C0. And maybe I obtain a new function V3 out of it. Okay, and I can do this again and again. Each time, so I start with an arbitrary function, I get a new function, I take this new function, I plug it here, I solve this problem, I get a new function. I take this function, I plug it in here, I solve this problem, I get a new function. So I get a function V1, V2, V3, v4, and so on. And what happens with these functions, I don't know, right? But my hope is that maybe it will converge to the function v that solves my original problem. So this, under some conditions, this is actually going to be the case, right? This sequence is going to converge. And this is called value function iteration. And under some conditions, this value function iteration will indeed converge, and this limiting function will indeed solve this problem here. And this is going to gives us a way in order to solve this problem in a general sense. It's not going to give us an explicit solution of the problem, but it's going to give us a procedure that actually we can implement in a computer in order to find the limiting, or to get arbitrarily close to this limiting function. And this is actually also something that we're going to do. We're going to implement this in a computer, this problem here, each time substituting the previous solution into the new right-hand side and converge towards the solution. And this is also a general procedure to solve this kind of optimization problems. But this is for later lectures. First, we're going to delve a little bit more into the mathematics of functions and function spaces and so on. This is for the next lecture. Thank you for watching.